All right, so then welcome to tutorial 2, where the goals will be to start with a brisk introduction to asocial reinforcement learning, just as a kind of starting framework. So here we're going to look at how we can simulate data in a two-arm bandit task, how we can do maximum likelihood estimation of model parameters, and we can start predicting choices. From there, we'll kind of scale up to various forms of very simple social learning models. For instance, imitating actions using a type of conformity bias, similar to what Lucy was talking about previously, combining this asocial and asocial learning components together using various forms, and then a bit of overview of a potential social learning hierarchy. And we'll also then talk about how we can scale to complexity along the 3 dimensions that Wataru introduced earlier today. So maybe you want to start with reinforcement learning.
Let me start from the very basic reinforcement learning task. So, okay, let me start from the non-social version of the very basic reinforcement learning task. So what is reinforcement learning? So that is, again, so imagine the very basic two-arm bandit task, right? You have multiple behavior options, and you choose one of the options and then got some reward. And then what happens when you got a reward? That is, you can update what you believe which is the best option. And then you can update your belief. And then, okay, in the next time, you can also, again, in the next round, you can choose one of these again. And you can then rely on this updated belief. So this recursive process, action selection and belief update, and then action selection again, based on the updated belief, is kind of sort of reinforcement learning processes. Let me start from the because I hate sticking with the boring abstract stuff. So let me start this with this cover story. So imagine this is the kind of farmer raising chickens, but he decides to plant some vegetables. But he might think maybe potato or maybe wheat, which crop might be better in this environment. He has no idea. Right. So now at the moment, so because he's naive in this environment, he doesn't have any strong preference, so he has no kind of prior belief, right? So what should we do? What should he do? Is that okay? Maybe just start from randomly, right? Just let's say he's choose potato for the first season, right? Okay, then he got this some pro reward. So pro means less than he expected, right? So he thought he'd get more, but potato might be a bit difficult to grow. So okay, then this result goes back to his belief value. Now he believes that, oh, maybe wheat is a better option to choose. And then he planted the wheat the next season. Okay, let's say he got a nice reward. So then, okay, this new experience now further go back to his belief value, and now he has an even stronger preference or belief towards preferring towards wheat, right? And then, okay, probably he choose wheat again. So this, the recursive process is actually basically like a two parts. It could be split into 2 parts. So one is observable part. Observable means that like observable from outside, like us watching him. Like we can only observe his behavior, like outward behavior, and also we can probably somehow guess how much he get, like from some partial evidence of happy face or sad face or something. So we can only observe this partial part of the story. So which means we couldn't always observe full story of what's going on underlying his decision-making processes, right? But so this is basically already a model that we assume kind of as a modeler, we assume that this could be one of the possible plausible processes that can account for the observed behavioral data. So now this the shaded area is totally hidden, right? But this hidden process, now we can assume that probably reinforcement learning process is underlying. So we can assume that these observed data was generated from this value updating and choice policy combination of these two processes would be the model of these hidden processes. So then, okay, what is these hidden processes? What is the kind of possible model of these reinforcement learning processes? So let me briefly show one of the simplest version of reinforcement learning model, which we will use in many other social learning version later on. So first, we need to think about what is value updating processes. So now here I'm going to talk about the Q-learning, so-called Q-learning, which is quite simple. So as I said, so let's say at time t1, at the beginning, he doesn't have any strong preference or no prior belief. We can think about, so Q value here defines the kind of this belief value, like approximately the amount, like how many crop he is expecting at this moment. So now let's say both potato and wheat has exactly same amount. He doesn't have any preference towards any of this. Then, so this updating process assumes that, okay, so original belief plus the new experience. So this, the new part, on the right-hand side is the new experience. That is like reward you got, reward he gets, and then minus the original belief. Right. So this is the so-called reward experience. I forgot the error. Reward prediction error. So this like error term is basically representing the gap between your expectation and the reality you got. So this gap, this error term is then weighted by this learning rate alpha, and then just combined to the original belief value. Yeah. Then generating the new belief state, easy peasy. And also, I need to note that the potato value doesn't change in this case at all. But this is already an assumption you made, right? We made, right? You can also think about what if potato value can also change somehow. So this is actually up to you, up to the modeler. It could, in theoretically, it can it's possible that potato value is also changing, especially for example when you haven't planted potato for ages, and you actually don't remember how much crop you got from potato in 20 years ago. You don't really remember, right? So this kind of forgetting process might change this potato value even though you didn't choose that option. So these are our possibility, but here we are just focusing on the simplest version. So belief value for unchosen option doesn't change, and only the chosen option value is changing. Yeah, and then more formally, we can write like this: Q value at the time t is updated to the Q value at time t plus 1 for action A, right? Action yeah. Then so now we have updated value or belief value, Q value, and then what we want is the process of action selection or the policy and action policy, decision policy. So policy basically defines the probability distribution over possible behavior actions. So in this case, we are only thinking about potato or wheat, so two unbounded. So either like probability of choosing potato, probability of choosing wheat. So that's on total, the decision possibility. So this is because it's a probability distribution. We want the sum of all of them should be equal to 1. So we have to have some kind of transformation into this original Q value, which is not bounded by this 1, 0, 1 scale, into this bounded probability. So the common way is assuming this so-called softmax mapping, softmax function transformation that is now as you can see, like Q value multiplied by new parameter beta, and that is the exponential of that is basically. So normally we have normalize all of them and then to bound them into one. So beta is sometimes called inverse temperature because it looks like a temperature parameter of the physics, but the inverse version in this case. Anyway, so now we have this decision-making probability for each options. Then simply we can use this model as a statistical process, statistical stochastic model. So assuming that next behavioral action is generated based on this probability, like a coin toss with a skewed coin in this case. All right, so yeah, let me talk about a little bit about beta value. So beta or inverse temperature controls the skewness or response towards your Q value, original Q value. So larger the beta value, so your as you can see, this choice probability function becomes more and more S-shaped, steeper S-shaped, which means that larger Q value, this decision maker becomes more and more exploitative, or like becomes more sticky to the option that he believes the best. Whereas like when beta value is small, like near close to zero, this decision maker's action is more like a stochastic or random, nearly random, not less dependent on original Q value. So then, so beta controlling this beta parameter, we can also express a range of this exploration and exploitation behavior by just contouring by this. But also, we also have to note that beta value and alpha value as well. So these two parameters are actually interacting to generate the behavior. So it's not, they are not totally independent. All right, so as we have discussed, we have a kind of code notebook in the website. And here, let me go back.
I would suggest that people do this offline because of just for the sake of time.
Oh, yeah. That's fair. Yeah.
So maybe I'll just say that we have a number of these kind of demos where you can play around the parameters, play around the task settings. I would say maybe this one you kind of do on your own time for the sake of time, so we can cover some of the content. But we will take a break to kind of look at some of the more interesting ones as well when we have the social components involved, right?
Yeah.
But this just lets you kind of get a feel for some of the intuitions behind what alpha and what beta do. Okay.
Yeah. Okay. So you can control a number of options and those parameter values, and then
I think I take over.
Yeah. Okay. So then
Great. Thanks, Wataru. So the code notebooks, by the way, like this, all the content contained in the lectures or in the workshops are also there, and there's math and code to go along with it. So kind of use that for kind of self-study on your own time. So Wataru has now presented kind of a very simple reinforcement learning model in a 2-arm bandit task, right? We have Q learning updates to learn kind of our expected reward that this farmer has for different options, and then we have a softmax policy to convert that into choices. So what do we need to then simulate behavior? Okay, so that's all we need to really simulate behavior. And we kind of showed you this in this kind of setting here, and we have some simulations that you can test out in your own time. So beyond only simulating behavior, we actually want to use these models to fit experimental data. We want to use these models to describe behavior in some experiments in the wild or in the lab. And to do so, we first need to define a likelihood function. Okay, so the likelihood is a probability of the data given some parameters theta. Okay, so some model parameters. Now, we can think about this in a very simple setting, like in a coin flip model. We're trying to learn the probability, kind of how skewed is this coin, okay? So we've observed some data, some heads or tails. This is actually a very old yen coin that I found, so I'm actually not sure if heads or tails, what that applies to. But we observed the number of heads or tails. And maybe a model that might be appropriate in this setting is a binomial model, right? So the binomial model has kind of two components. One, we're trying to model how many flips. And then theta is the probability of heads, okay? And so here are four different situations you might be in. One situation where you flipped 3 heads, 7 tails, one with 5 heads, 5 tails, etc. Now, this is where we've kind of put that information into our binomial model, okay? So each of along the x-axis here, we can have some kind of probability of heads. So if we have observed 5 heads and 5 tails, the likelihood of the true probability of that coin yielding a heads being 0.4 is indicated by this red line here, right? So that's kind of the y-axis. That's the likelihood, okay? So that it's more likely, right, that that the true probability is 0.4 than maybe something else like 0.8, if given that data, right? Although the most likely situation is probably that it's 0.5, okay? That's known as the maximum likelihood, and we'll come back to that a bit later. So for multiple data points, we're trying to model not only a single decision, but multiple decisions, like a farmer over multiple seasons. And for this, we need to describe the joint likelihood over all observations, okay? So the joint likelihood is the likelihood for each observation multiplied against all that likelihood for each of those choices. So this is this product here. Now, it's much easier to compute this using logarithms, since we can simply replace multiplication with summation in log space. And so for this, we use the log likelihood, right? So we sum over the log of each of these likelihoods, okay? Now, since probabilities are always less than 1, the log likelihood will always be negative, okay? Thus, it's more convenient to express this model fit using the negative log likelihood. So this is a concept we'll be using time and time again now. So we simply invert the sign. And what this means is that we're able to express the amount of error or loss, right, using this negative log likelihood. So the larger it is, the worse our model fits, okay? So smaller values thus describe better model fits, the log likelihood. Okay, just a little note here, I'm using the term log. Everyone uses this, but typically by default, people use natural logs. You can write this also using ln rather than kind of the base 10 logarithms. But this is just a general convention. For people kind of encountering this for the first time, this might not be intuitive. Good. So we can think about these likelihoods as providing some notion of goodness of fit. Let's imagine we're taking some money, we're going to the casino, or going to a pachinko machine place, trying to bet our money on what kind of actions will result. And we're trying to do this as effectively as possible, right? So our likelihood here, for instance, if you have some parameters in the model that's giving us an 80% chance of heads, 20% chance of tails, we're betting on this outcome, right? So of course, we convert this to a log likelihood. We get these numbers here. And then the negative log likelihood is a bit more intuitive, right? So we have a loss of 0.22, which is not bad if we had heads. And we have a loss of 1.16, which is much worse if we get a tails, right? So we really hope that we get a heads result, right? But because we don't know what's going to happen, we don't want to bet too risky, right? You don't want to bet all our money on one because then you would potentially get infinite log loss if the unexpected outcome occurs. Now, one more term, just because we haven't had enough forms of likelihood here, is called the deviance. It's simply 2 times the negative log likelihood. And this you'll see come up in the BIC, AIC computations as well that we'll present in the final tutorial on, I think, Thursday. Okay, so just so you're familiar. So from these model simulations, it's actually very straightforward to produce likelihood functions. So this is a very important kind of intermediate step when you're doing modeling. And in practice, we can use code that's very similar to our model simulations to create a likelihood function. So in that demo we just skipped, we also developed some simulation code that you can play around with. And for the likelihood, we just have to kind of wrap that up a little bit. It's actually very straightforward. That, for instance, I give examples in both Python and R. But for a model, we define a likelihood based on a set of parameters, and then we return some negative log likelihood. Okay, so we give the likelihood function parameters and data, and we return a negative log likelihood. So how do we do this? Well, we first initialize our negative log likelihoods p0, and then we loop through all our data. Our model is making predictions for every time step. And then for that the choice that we actually observe, we take the log of our prediction, and then we keep summing that up to get the negative log likelihood and return this. So in practice, what we're trying to do is to figure out, okay, what set of parameters will give us good fits? And we want to kind of use those to then give our model the best chance. So this describes what's known as maybe the simplest and most common method of model estimation, which is known as maximum likelihood estimation, or MLE. So recall our likelihood function here. We're using this likelihood function to find the parameters theta hat where the likelihood is the largest. So for instance, with our coin flip example, right, if our data gives us 8 heads and 2 tails, then we might estimate the parameter theta hat of our binomial as being 0.8, right? Because that's the most likely. Now, this highest likelihood is also where our negative log likelihood is lowest. So in practice, we're going to try to minimize the negative log likelihood in order to maximize our likelihood. Okay, so be careful. There's some flipping around that. So in practice, again, we have this likelihood function we talked about. And typically what we do, whatever programming language you're going to be using, we'll wrap this in some sort of optimization function, right? When we use this to try to figure out what set of parameters theta hat will give me the best fit. So we can imagine maybe this is our loss landscape. Maybe our model has 2 parameters, like the Q-learning softmax model we just showed. So then theta 1 would be the alpha learning rate, and theta 2 would then be the softmax inverse temperature beta. And we're trying to figure out where in this landscape is going to get us our lowest point, our lowest negative log likelihood. And there's a whole range of possible optimization algorithms you can use here, right? Such as gradient descent, simplex methods, which is kind of like some sort of geometric shape rolling down the hill, or various forms of differential evolution, which kind of is a form of swarm optimization. But just be very careful here that none of these optimization algorithms are ever guaranteed to converge on the globally best solution. Notice how this loss landscape has all these local optima, right? So these are all potentially likely to get stuck in some situations. So there's a whole range of techniques for kind of how to improve your fits. For instance, running your optimization multiple times. These kind of more complex methods like differential evolution are more likely to get you better fits. And we'll cover this again in some later sessions. But also, these are open questions. Everyone's trying their best to try to find the best maximum likelihood. Okay. Good. So let's think about how we can do this for a reinforcement learning model. Recall that Wataru told us that we only have access to the observable choices that the participant makes. Some situations we also have access to their payoffs, but here let's just say we only see their choices. So let's imagine this is kind of a more complicated bandit task. There's 3 arms. These are their choices over time. And from this, we're going to be searching for parameters of a reinforcement learning model that give us the maximum likelihood, that give us the best fits, right? And so this could be one example where once we've estimated the parameters, these kind of color bars represent the net choice probability from that model, right? So that's equivalent to kind of what the model simulation would yield us on that set of parameters in which we've estimated, okay? So again, with our kind of 2-parameter Q-learning agent, again, you'll find this in the notebook. Here, I plotted out what the loss landscape looks like. So I've generated some data based on this combination of parameters at this square. And then I've run kind of the model at all these different kind of gridded values of combinations of beta and alpha to kind of give you an idea of what the landscape is like. So we kind of have these very steep gradients in this kind of very nonlinear way. And then the best estimate is actually not exactly at the true parameters, but quite close, right? And this shows you something about the fact that choice behavior is stochastic, and the maximum likelihood estimate is never guaranteed to give you exactly the true generating parameters. There's always going to be some noise in this process, okay? And so this is an idea of kind of what that loss landscape looks like and how the lowest values are kind of quite close, but it's still quite a lot of variability. Different models, of course, will have very different parameter kind of loss landscapes, and also different tasks will as well, and that interaction plays a very important role. So it sometimes makes sense to kind of better understand what kind of environment we're dealing with to figure out what optimization methods should I use, or what types of model fitting procedures are most appropriate. Good. So here we've talked about kind of parameter space, like so given a single model, how do we find good parameters? And the simplest possible method is to use maximum likelihood estimation. But of course, we don't always only have a single model, right? Often in science, we're trying to figure out which model is the best fit for the data. And in these situations, we kind of have a whole space of models, right? That might vary in a number of different dimensions, such as the structure, but also the components, right? These models also may be related to one another. And that's why I've used Lego as a bit of an analogy here, right? They might have similar components as well. And so we also will, in the final tutorial, we'll do much more of an involved look at how we do selection across different models and model comparison. But keep in mind that this estimation is really for a single model. Okay, good. So I think we have enough time for maybe the first learning for social, some of the early social learning methods, and then we'll break for coffee
Yes,
at
yes.
15.
Yeah.
Okay. So that was a very brisk introduction to reinforcement learning. There's a lot more details in the notebook if you want more about that. But now we're ready for some social information. Okay, good. So again, we have our farmer Wataru. He can learn from experience and plant, but maybe he can also learn from social information as well, right? Maybe he has a very kind farmer neighbor who can also potentially be used as a target for social learning, right? And using their behavior to also inform what behavior he should do. So we're going to start with perhaps the simplest form of social learning, and kind of already saw this in the great tits and cognitive, and I think in some aspect of cognitive as well that Lucy was discussing, and this is to imitate actions. And one very simple form of this is a type of conformist bias, right? So this is called frequency-dependent copy. So here, a very pure social learning behavior could be to kind of choose your actions to kind of develop a frequency-dependent copying policy here. That's simply you're choosing actions proportional to how frequent other agents perform the same action. Okay, so this F is just a frequency, and this policy can simply depend on the popularity. Okay, so we're more conforming towards the more popular actions. Here we might have a parameter theta that's known as a conformity exponent. So the larger this exponent, the more conformist we are. Okay, where smaller values mean that we're also more likely to choose the second or third most popular option. Okay. Now, this type of very simple kind of conformity bias also helps illustrate some of the wisdom of madness of crowds that Kameda Sensei was talking about in the morning. One kind of phenomenon that kind of illustrates this quite well is known as Rogers paradox, where this helps illustrate the fact that social learning via imitation has frequency-dependent fitness, meaning that how good I am, how successful I am when I imitate really depends on what everyone else in the population is doing. So let's consider a very simple situation where the fitness of individual learners always remains the same. Okay? Now, the fitness for the social learners in blue is really going to depend on the frequency of other social learners in the population. And here, the social learners are just doing imitation. Okay? So when no one else is doing any social learning, everyone else is doing individual learning, this is great. A lot of prime targets for copying and for scrounging off of, right? I have a very high improvement in fitness because I don't have to pay any of these costs for individual learning. I can just copy off of my neighbors. But as the number of social learners in the population increases, then what we have is just a kind of this cascade, maladaptive cascading behavior, right? We're just copying other copiers in this kind of endless chain. We're just copying noise at that point. And then for these social learners, fitness is much, much slower. Rogers paradox helps illustrate that in this very simple situation, right? And there's many other kind of adaptations and extensions of this framework that lead to different results. But typically, we find that we get some intermediate mixture of individual social learning that evolves in this kind of evolutionary stable strategy, okay, in this type of setting, right? So this helps illustrate that your kind of benefits for social learning really depend on what everyone else is doing in the population in this very dynamic optimization problem with game theoretic dynamics. So maybe we'll actually do this demo because I think this is quite cool. So here in demo 2 from the code notebook, I would suggest that you take a look. So I can also navigate it to you as well. And here we have these really cool demos. So notebook 2, and I will go to learning from social information, imitating actions, and demo 2. So here you can, hopefully this runs. We can control the number of options in our bandit task. We can control the number of agents, and you can control the number of social learners. Okay, so this number also should be never larger than the number of agents, or I might throw a bug. And we have the learning rate of our agents, our inverse temperature, and our social conformity in a number of trials. And then you can simply hit run, and we'll see the results plots, right? So here we see the performance of our individual learners, the performance of our social learners, and their average rewards here. And so what you can very much see is that as you kind of reduce the number of social learners in our population, we'll also reproduce Rogers paradox such that the social learners should perform better. I think I also kind of have some unusual learning rates as well. So you have to play around these parameters. So these parameters will also kind of play a role. But in general, you can kind of reproduce Rogers paradox in this bandit task as well. And the code for that, if you click on this code button, is available there. Okay. So maybe take a moment, and then I'll return to the talk slides. Okay, pretty good for time, so maybe keep going until 3:15. Yeah.
There's like a demo server, it's like busy right now, so.
Yeah. So this is so the demo server also at some point will be overloaded. So if it's not working now, you can also come back to this time. They're always online. Cool. All right. So then maybe I'll move on for now, right? But then you can kind of see the main illustration. So we showed you the simplest kind of social learning strategy. That's kind of a pure social strategy. But of course, we don't only do social learning. We also kind of integrate social and individual information together, right? So here we're going to present one very simple way that you can do this. And this is can be called decision biasing. And this is a term I think Wataru used in his 2019 paper. And here we might describe this as a very simple mixture policy, where we mix our individual policy based on kind of this Q-learning of softmax approach we first presented, together with this frequency-dependent copying strategy we just showed you, okay? This pi-soc. So pi-int and pi-soc are mixed as a function of gamma, where 1 minus gamma is the probability of playing our pi-int strategy, and gamma is the probability of playing our pi-soc strategy. So this mixes together, and it leads to kind of social information influencing our policy. And so this decision biasing is a way that we kind of take our kind of asocial reinforcement learning loop and integrate social information at the level of policy. Okay, and we'll come back to this later and introduce other alternatives as well. Okay, so again, we have a demo now here with our decision biasing agent. But I think because of the server load, maybe I'll let you kind of do this on your own time. But again, here you can play around with the different parameters of the agent, where I think the key one to kind of try is the social mixture. And you can kind of see how this population of agents performs and is influenced by these parameters. Okay. Now, social learning doesn't necessarily only influence us at the level of policy, right? They can also influence us at different levels of our kind of internal representations. I think this is something that makes particularly human learners quite unique, right? In making us so incredibly capable of learning on a cultural level in a way that no other animal is really able to do. I know this maybe gets some pushback about what exactly differentiates humans from other animals in terms of cultural learning, but there is something quite unique about social cultural learning, especially as here in a city like Tokyo, with the kind of the massive skyscrapers and infrastructure that we see here. People like Kevin Leyland, I think in one of his latest books, said that sometimes he vacillates between wondering whether or not humans are really that different from other animals in terms of cultural learning. But then he remembers we build cities, we send people to space, we build these, we can have a summer school spanning who knows how many countries and institutions, right? So something is really quite special about human social learning. And this also maybe can be partly explained by the fact that we can also integrate social information to multiple levels of our decision-making process. So here we've shown how decision biasing can influence kind of the level of actions or policy. But we might also have other types of learning, for instance, value shaping or value inference via theory of mind, another way to say emulation, where social observations influence our value representations. And this maybe lets us deploy that information in a more flexible way, right? For instance, with different choice sets, okay? When we can only imitate people in the exact same context in which we see that behavior, but in a different context, value is maybe more generalizable. And even maybe more complex, we can do types of model-based theory of mind, where we're not only inferring people's values, but we're inferring what their structure in the environment is, or what their own individual reward preferences are. That maybe lets us generalize even more, more to kind of diverse settings and leverage that social information even more effectively. So we're going to first start with one of the kind of a very simple form of value-based social learning, where the social information influences not the policy, but the value representation. And this is called value shaping, and it's very much informed by previous work on stimulus enhancement. by others, and this is based on a more recent paper by Najjar et al. And here, our farmer Wataru maybe isn't being influenced by his neighbors at the level of policy, but based on his value functions. Wataru is a very clever man, and he's maybe kind of tried to use the social information more effectively. So here, we might update our Q values based on some sort of value bonus based on the frequency of what his neighbors are also doing, right? So he maybe has more neighbors planting potatoes than wheat. He might then assume, kind of to overcome his initial naivety as a farmer, that, hey, maybe potatoes are just better and more effective crop to produce. And he generalizes at the level of value as opposed to policy, okay? And this paper by Najjar et al. Already shows that there's kind of different distinguishable behaviors from decision biasing and dire shaping as well. And here we have one more demo where you can try out heterogeneous groups of both individual learners, decision biasing agents that integrate social information at the policy level, and value shapers that integrate information at the value level. Wataru, do you think if people try out different demos, that might spread the load a bit on the server? Yeah, okay. So maybe what I'll do is I think this is a natural stopping point that maybe people can spend a few minutes trying out the demos. Hopefully that kind of spreads the server load. We're going to then start a coffee break, and we'll come back at 3:45 for the second half of this tutorial. I'm also going to suggest that during the coffee break, please find your mentor so that we can have the mentor groups form, and then you can start discussing what types of activities you might want to do during the mentorship session tomorrow afternoon.
Yeah.
Okay. And again, if you don't know who your mentor is, maybe talk to me, Wataru, or Henri to be assigned. But you should have already received an email like we asked. Okay. Just a quick show of hands. Does anyone not know who their mentor is? Okay, so solved.
Cool. Also, like Mayuko Nakamori. Mayuko is not coming today, unfortunately. So she comes from tomorrow. So those Mayuko's group, you can also come to me, and we can also talk about like I talk with Mayuko tomorrow.
And Shinsuke is also.
Shinsuke is here.
He's here.
Yeah.
Okay.
I saw him.
Okay.
Okay.
Yeah, but don't worry. I was like, so we'll figure this out, and then also feel free to kind of do everyone make any announcements? Lunches about
lunches
will always be at the Hirosawa Club now.
Yeah. Sorry about the mess with the lunch. So lunch is always at the Hirosawa Club, the venue today. So for tomorrow. Lunchtime, we all go to that venue. Yeah. Okay. Cool.
All right. Then we'll take a little break now, and then
see you 30 minutes.
That's good. Stop the recording, and then we'll start it again. Yeah, pause. That would be great. Actually, is that record? Are you recording? Okay, great. So welcome back, everyone. For this kind of second half of tutorial 2, we're going to talk about how we might scale up to more diverse social learning tasks, again, using this taxonomy that we introduced in the first tutorial. For the interest of time, I can't cover as many kind of forms of complexity as we introduced, so we're going to focus kind of on one or two along each dimension. So first of all, in many types of environments, right, rather than assuming that each action has independent rewards, that the rewards of planting wheat are completely independent from planting potatoes, typically we have some structure in the environment that we can leverage in order to generalize from some familiar set of situations we've experienced to a large range of new situations, okay? And so this forms a distinction between what kind of two different approaches to RL. One we can call tabular methods. So this represents this kind of to our embedded tasks, the options are completely independent. And our Q-learning model, right, which learns separate reward expectations for each option, but for something we've never experienced before, just defaults to some prior, okay? And it's illustrated here by the bars that the options are assumed to be independent. But in contrast to this, in many types of environments, from our farmer actually planting crops or foraging for resources like mushrooms, rewards tend to have some sort of spatial structure, right? Crops planted next to each other might perform similarly. Mushrooms often grow in patches or clusters in the environment, right? And so we can potentially exploit this using a different form of reinforcement learning methods that use function approximation, right? So one framework in which I've studied this is the spatially correlated bandit task that Wataru introduced this morning, where here the tiles on the grid are each a different arm of the bandit, but we've enforced a type of spatial structure that can be used and exploited in order to search more efficiently. To do so, one approach is a Gaussian process model. This provides a very versatile framework for regression, for generalization using a type of Bayesian function approximation, right? So given a small number of observations of reward, so these kind of little dots, we can then form Bayesian predictions about the expected reward, this blue line, and the uncertainty as well involved assigned to each of these options, right? Where remember from Kameda-sensei's talk this morning, that kind of uncertainty plays a really important role in figuring out when I should learn from others, and also how effective my information is in kind of pulling towards wisdom of the crowd effect. Okay. So this can also be applied to a wide range of settings. So not only in the kind of spatial situations based on kind of assuming that stimuli in similar locations will yield similar rewards. We can also apply this to kind of any types of arbitrary features, right? For instance, trying to come up with new cooking recipes where similar combinations of ingredients are typically going to yield similar flavors. And we can also even apply this to network connections as well, right? Where maybe your friends in your social network that are connected to each other are maybe more likely to have the same kind of tastes in music or cinema or in art. Okay. So here I've also provided some code examples where using, again, a bandit task, so here are 25 armed bandits, I've given both this kind of tabular Q-learning model. We've introduced so far a set of these observations in these orange diamonds, and a function approximation approach using the Gaussian process model, the exact same set of observations, right? And so here, these reflect the beliefs of the model about the environment, given this limited set of observations. So here, the Q-learning model just kind of defaulted to 0 for any option that hasn't experienced before. And the reason these blue lines aren't all the way to the orange diamond is because the learning rate is not 1. So this is going to only partial learning. And the Gaussian process model here is able to kind of use the principles of interpolation, extrapolation to then predict and generalize about other options, such that maybe some option here that we haven't tried yet is maybe the most promising thing to search next, right? Rather than just flipping a coin or choosing randomly based on what we observed before. So here we have some code that you can maybe play around with afterwards to also test this. Now, in a social context, social generalization is also very important, right? All of you here have different preferences, different goals, different skills. And when we're using information from diverse individuals, sometimes we have to kind of use this information and take it with a grain of salt, right? We can't necessarily take it from verbatim, right? And so in some work that was done by Alex during her PhD, which she just submitted on Friday, congratulations, Alex, tested this socially correlated bandit task. Okay, so in this situation, we have a number of scientists who are searching for samples in this alien ocean, and each of them have a different target that they're trying to search. So they're not having the same reward functions, but they have some correlations between them, right? So for this scientist here, the target player, the best options are maybe over here, and they're not exactly the same as the other people that they're also able to see observations from, but they have some similarities, right? Typically, this corner here is very bad for all of them, etc. So you can still use social information to learn faster, more effectively, but you can't take it verbatim because people have differences between people. You can read the paper for the full details, but here we tested a number of different social learning models, including the decision biasing model we introduced, value shaping, and then this new form of social generalization, which uses social information and generalizes it to inform our beliefs about the world, but doesn't do so verbatim and takes it with a grain of salt, assumes that it's more noisy. And here we show that's more effective at both kind of normatively performing well in the task via evolutionary simulations, and also providing the best prediction for human behavior in 2 online experiments, including 1 pre-registered replication, where in all the group rounds, this provided the best predictions for human behavior. Okay. Furthermore, let's look at the social complexity dimension, where here we're going to focus on network structures. So Wataru already teased this a little bit, but a lot of past work has looked at how kind of different network structures kind of influence the flow of information between individuals in a group, right? And one general principle is that the kind of the connectivity of the graphs influences the flow of information, and thus also influences the amount of diversity of solutions that are available in the population, thus influencing the exploration and exploitation dilemma, right? So in these kind of very restricted, locally connected networks, we have a much slower flow of information. And the trade-off for this is that we might maintain greater diversity of solutions and behaviors that are observed in the different nodes in this network. This then leads to more exploration at the group level, right? And in some certain environments where more exploration is required, this actually leads to better performance. In some other situations where these fully connected networks, the flow of information is very rapid, and this leads a collective to converge very quickly and leads to more exploitation at the group level. So here, the optimal balance really depends on both the environment and the task. So for instance, some past work by Mason and Watts in 2012 studied this kind of single peaked environment, which also had a bunch of noise, Perlin noise introduced as well. And here, their kind of take-home message is that, hey, fully connected networks lead to better performance. Yet at the same time, people like Laser and Friedman and others were using these NK environments. These are these high-dimensional environments, combinatorial environments. So here, each of these dots represents a binary string, and I've connected the binary strings together, so the nodes together for kind of neighboring solutions, where a single edit leads to the other solution, okay? So that's how the way this network structure is. So this is very high dimensional. The K, so N stands for the dimensionality of the environment, and K stands for the amount of interdependencies, right? So you can have things like, for instance, when you're choosing a basketball team or a soccer team, you don't only want the best players on the team, but you also want good synergies between players, right? Certain players jive better with one another and lead to something more than greater than the sum of the parts. And that's also a principle that's built into these environments. So this makes them very difficult to optimize because they're very complex, high dimensional, and combinatorial. And in these types of environments, these locally connected networks were observed as being best, right? So here, because these environments can be interpreted as kind of manipulating the exploitation dilemma at the group level, the best types of networks also depends on the type of environment. And similarly, this also depends on the types of tasks as well. Some work by Maxime Derex and others have looked at how network structures influence cultural evolution, where cultural evolution is being studied as really highly combinatorial tasks. So these types of alchemy experiments where you can combine or recombine these different potions together to kind of achieve really complex solutions that require many generations of innovation. And here they found that these moderately connected networks perform best. These highly connected networks converge too early and exploit some suboptimal solution, whereas these moderately connected ones maintain greater diversity of solutions across the population, leading eventually to higher and better performance. Okay, so these kind of cultural innovation problems often are more similar to these NK environments and often are benefited by more restricted social networks, is one kind of the principles, although this is kind of so moderate. You can have far more restricted in there. It's never good in these sets of situations. So again, you can take a look at the notebook. I programmed some simulations here using, again, a multi-arm bandit task. But here we have our agents. I think I'm using a very simple decision biasing strategy, if I recall correctly. And they're either in fully connected networks or in these locally connected ring networks where the K parameter controls the number of neighbors that they have access to. So here they have 2 neighbors they have access to. And on the left side, I have the fraction choosing the optimal arm, and the right side is the mean reward per round. And what you can see is that these kind of fully connected networks converge too early on a suboptimal solution, whereas these locally connected networks continue to keep exploring and finding better solutions and converges later, but converges at a higher level. And you can also, again, take that code and kind of play around the parameters on your own and try out different solutions. Now, of course, these kind of networked simulations are kind of highly synthetic and artificial. And I think it's great that kind of Lucy's work, Lucy's talk preceded this tutorial because she kind of demonstrated how in the wild, these types of kind of social interactions are much more naturalistic. They're not explicitly structured, but rather evolve over time and dynamically through a variety of social and environmental factors. Thus, there's many open challenges for how we can infer dynamic social interactions using a variety of different technologies that we have. For instance, some classic work by Ariana Stromberg-Peshkin used GPS collars to track these baboons, looking at how they kind of collectively make decisions about where to forage for resources. Some more recent work by Damien and Lucy have been exploiting Apple's Find My phone or Find My network using these kind of small Bluetooth tracking chips to then try to infer these social networks of various birds. Some work that came out of the University of Constance, where the previous two Cosmos summer schools took place, include this T-Rex method, which uses machine learning tools to use camera-based pose estimation. So some recent work that has used this approach, for instance, you can has taken separate autonomous drones using camera video of these. I think these are gazelles. And then from that video information, and further pose and further social interactions, and then from that develop social network analyses. So very kind of cutting edge approaches that leverage advances in machine learning. And a much simpler approach that I've used myself is designing experiments in virtual environments, such as in the game Minecraft, where because of humans can kind of take instructions, can play games, we can then also very simply simulate their entire field of view, where we've mapped each event, each player, each object to a unique RGB pixels, such that we can simply read off the screen at any point in time and figure out which players were visible to build these kind of dynamic social networks, which events were visible, which blocks were visible, to then integrate into a more complex social kind of computational model, integrating both individual and social learning as well. Cool. So then moving forward to the cognitive dimension of complexity. So far we've talked about only very, very simple social learning mechanisms. Someone was talking to me in the coffee break about how can these methods be used for coordination, right? They seem too simple. And I think the answer to this is that often coordination and collaboration, we require a more sophisticated form of social learning based on theory of mind inference, right? So the basic idea behind theory of mind is that we can take this observed actions that we see from other people and then infer imputed mental states. And this is very similar to the exercise and modeling that we're doing here. We're observing participant choices and we're inferring something about their decision-making process. And that's exactly what theory of mind is trying to do. Right, so this is known as theory of mind. It's called emulation. And this is often modeled using a type of inverse reinforcement learning. This is very similar to the type of modeling we're talking about, where we observe someone's actions, but we don't have access to the values or beliefs or intrinsic reward structure that gave rise to that behavior, but we want to infer this instead from that action, okay? And we can specify this based on at least two different levels of social learning, according to one of my frameworks, although feel free to disagree with that. At the very kind of simplest level, exactly the exercise of estimating a Q-learning model, right? Farmer Wataru, we see his actions behind what he's planting. He's planting a lot of wheat. I might infer that he has a higher value for wheat than for potatoes, right? And this is done in this kind of Bayesian formulation, most typically, where we're trying to then, where we assume that he's going to be selecting actions that are more consistent with his value representation, right? If he's planting wheat, then he's probably going to have a higher value for wheat. Which we integrate to some sort of prior over his probabilities that his value functions for wheat. But in addition to this type of value inference, we might also kind of do more sophisticated forms of social inference. And I think for types of collaboration or competition or coordination problems, these more sophisticated forms maybe really play a more important role. And one way to think about this is kind of consider this model-based distinction in reinforcement learning. So we might not only learn value representations, kind of which are independent of context, but model-based representations, for instance, about the individual's beliefs about the structure of the world. Here we're using the term model, not in the sense of model-based imitation that people like McElrath and Boyd and Richardson have typically used, but in terms of how reinforcement learning people talk about model. Okay, so here in reinforcement learning, a model is an internal representation of which states and actions give rise to which future states and which rewards. So we're trying to model the environment internally. Okay. So I might close my eyes and I'll maybe have a model that all of you will still be seated here, paying close attention to this tutorial, because I have some expectations about what is going to follow, right? And this is in contrast to model-based imitation, which is where focusing on kind of who to copy, okay? So here, based on the actions of another individual, might also infer something about their structure, their beliefs about the structure of the environment, something about what their causal representation of the world is like. And that might also help me generalize more effectively into new situations. And this also maybe involves inferring their intrinsic reward specifications, right? The behavior of someone else maybe reflects the fact that they prefer broccoli or healthy foods over junk foods like donuts, right? And I might still use information more flexibly if I'm someone who actually prefers junk food than healthy food. I might kind of learn from their behavior in a more flexible way than just imitating their choices, given that we have a misaligned reward specification. We'll talk, I think in Leo and Kartik's tutorial, we'll talk more about various forms of theory of mind. But here I just wanted to point out that theory of mind, of course, can be instrumentally useful. Sometimes we use it to then get more from the social observations we observe. You see some behavior, we learn something about what that person's beliefs are about the structure of the environment, and we can kind of go further with that than just imitating their actions. And this is often more flexible, right, than choice imitation, where choice imitation is somewhat inflexible to different skills, preferences, and goals. So for instance, if you copy the moves of a professional skier, you might find yourself in the hospital, given this mismatch of skills. If you copy the food preferences of a carnivore, but you're a vegetarian, you might find yourself in a restaurant where you can't eat anything. And if you follow a random car in the streets, you're very unlikely to reach your own destination, right? And so in these situations, imitating the choices or the actions of someone else are far less flexible than trying to infer something about their values or beliefs that give rise to the action. But in addition to kind of the instrumental usefulness of theory of mind, it also plays a very important role in pedagogy as well. So pedagogy is where teaching involves teaching someone else, trying to effectively teach them. And often, effective teaching requires inferring what the learner knows and what the learner doesn't know. In putting together summer school, I already kind of have an idea. I've read all your applications that people come from very different backgrounds, right? And this has also kind of helped guide how I put together these lectures to kind of make sure that I'm trying to select as informative as possible bits of information to give to you to kind of keep you, to teach you new things, but also keep you engaged if you're kind of more advanced. Right. So some past work by Natalia Velez has showed that kind of effective teaching involves inferring what the learner knows, and this has also been verified in fMRI scanner experiments as well. And here I wanted to point out that pedagogy plays this really important role in cultural transmission, right? So trying to scale up to culture here. In this great study by Morgan and al, they used a very kind of ecologically valid stone napping task. So stone napping is kind of a very ancient technology that is very foundational for the origin of our species, where you kind of taking stones, hitting them against one another to produce a fine edge. This is very difficult to do. And they considered different transmission chains, right? One where people only saw the final product and had to try to reverse engineer it themselves. Situations where people were trying to imitate or emulate a demonstrator. And then a range of teaching behaviors from very basic teaching to gestural teaching, where they can also kind of show on the target flint where to hit, and then verbal teaching using language as well. And here's just one of the many plots from that paper showing that this kind of increasing degrees of pedagogy, it led to greater and greater quality of the final products being produced as well, right? So this form of pedagogy involving theory of mind and inferring the beliefs representations of the learner plays a really important part in cultural evolution. And then I'm going to try to kind of see if I can put it all together a little bit in the end. So I think we still have many open questions regarding how we might model cultural evolution. I'm going to point out maybe one strand of my research that's tried to kind of put all these ingredients together, although I think we're still far from really understanding this at the greatest level. And I think this is a real source of open questions for our field. So one setting which I've tried to kind of apply all these principles of modeling is on a data set from this game called 1 Hour, 1 Life. So this is a real game. People pay money to play this, but the creator has open sourced the data. And this has been an incredibly rich source of data for us to understand some of these questions. So players live a virtual life in 60 minutes. They're initially born to a random player who's already online in the game. And they're initially dependent on an online community to then survive until adulthood, right? So each minute in the game is 1 year of virtual life. And in this 60 minutes, people make very, very small incremental improvements that leads to really large-scale technological progress over many, many successive virtual generations. So what's really nice about this data set is that it allows us to kind of bridge two dimensions that are typically orthogonal in this type of research. Many lab studies have very, very complete data, but the richness of the communities are quite limited. They're relatively artificial or very simple. In contrast, field studies are able to tap into the kind of the real world richness of real world human communities, but often have very limited data in these situations. And that's where this online data set has an advantage, is that we have data from 430,000 avatars over 127 million interactions. Here is a tiny, tiny fraction of the total map size from here, played out over a small fraction of the data that we have, showing you just a very, very small kind of sliver of the full complexity of the data that we have access to. And these kind of rich communities defined by family relationships as well. And this data set allows us to try to understand technological development in the microcosm. So here I'm going to be careful not to use the word culture evolution, because here there's a predefined set of technologies based on a tech tree. Culture evolution is open-ended. I think that's a very important distinction. So we're framing this in a more limited sense as technological development. And one nice way to illustrate this comes from an anecdote that we found in one of the game forums. So I'll illustrate in a second. So in this game, you're really literally putting sticks and stones together that over a kind of large successive range of very expansive text tree. You become able to produce much more technologically complex technologies like a camera. And this and to be able to take a photograph, which requires combining 528 unique components together. So this anecdote I was alluding to earlier from the forum is about one of the players talking about how they spent their whole life entirely dedicated to taking a picture. They already had the camera, so they were already at this point, right? Really, really far along the tech tree. So they only needed, so a huge chunk of the work was already done. I just needed to make some silver nitrate, some paper, and a black cloak, right? So that's kind of the remaining components that were necessary. But by the time the silver nitrate was finished, I was an old man. So then I explained the process to an inquisitive young girl who wanted a picture. And I hope that at some later point in that kind of long story of technological evolution, someone was able to take a picture. Okay, so how do we approach modeling such a rich and complex data set? So one of the tools that we tried to developed was try to find some way to quantify and define what jobs do people perform in the communities. So we had this massive data set. So there's like 500,000 rows of different avatars. And then there's, I think, thousands of items in the game, right? So we first developed this matrix where we have counts of which players interact with which objects. And we used a method called non-negative matrix factorization to develop a way to kind of develop some sort of semantically interpretable latent representations of the players and the items. So we developed, this allows us to kind of define a small number of latent dimensions. So for instance, the farming dimension was well defined by items like fertile soil, carrot pile, steel hoe, whereas baking was defined by interacting with items like pie crust, hot adobe oven, bowl of flour, etc. And then from these, we can then embed avatars in different locations in this high-dimensional space, different players. And we can also embed items as well. Here's a T-SNE plot of our item space. And one kind of analysis we were able to do with this data set and these kind of latent representations of jobs is that we can model the cultural transmission of expertise. So on this x-axis here, we can model social influence based on the frequency of interactions with some target player and their job dimension loading for that specific dimension. Okay, so this allows us. This is based on kind of this interaction structure, these interaction network that we were to develop from the data. And on the y-axis, we can look at kind of how much they adapted from one life to the next. So we can look at how what their job vector is in the current life minus their previous life. So this allows us to control for individual differences in terms of some players like generally to be a farmer, some people like to be a baker. We can look at how their interaction structure shapes their actual choices in their life. And this allows us to kind of find this very nice kind of neat linear relationship between social influence and individual adaptation across all these dimensions. And we also be able to account for a number of other factors as well, such as the kind of the total amount of social influence, the number of interactions that they had, and how long they played the game. And we've also been able to compare this to alternative models where we randomize the job vectors, where we randomize the network as well. And these all have much worse predictions. But in addition, we can also try to understand things like how do different characteristics of these communities affect technological development, where specifically we're looking at kind of two factors based on specialization, interactivity, although we've also looked at a whole range of different network properties as well. But these ended up being the best predictors. So specialization is based on this kind of economic variable called the Herfindahl-Hirschman index, which essentially looks at kind of how much diversity there is in the different jobs within the community. So for instance, in this family, we have very low specialization because there's very high diversity of job embeddings. Whereas this family is very specialized into foraging, where many people all share this as their same highest loading. And then our interactivity captures something about kind of how often people interact with the same object, right? And this allows us to capture kind of the degree of social interactions. And here we wanted to understand how these characteristics affected kind of two main forms of technological development. So one is effective repertoire size, how many items are being interacted with in a given generation. And then the second is stability, how much overlap is there in the items interacted with in one generation that's also interacted with in the next. Here we define generations based on these kind of 20-minute epochs of the data. And here I'm also going to split the results based on population size, because kind of classically, we all know that population size is one of the main drivers for cultural evolution, or kind of the transmission of technologies. And here we find, here are our findings. So interactivity in both situations, both increases effective repertoire size and stability, but we have an inverse relationship with specialization. So highly specialized communities have less diversity. They actually have smaller effective repertoire sizes, but they have higher stability. They can kind of carry on these technologies more stably from one generation to the next. Now, beyond only predicting technological developments, we also want to predict what types of factors influence the eventual and future collapse of these communities. So can we try and predict when these communities will collapse, when the population size will go to zero? So we control for a whole range of factors, including like what time of day people play, etc. And we have all these are the raw variables that we're interested in analyzing. We kind of align them to the time of collapse, time zero. And then we do this temporal cluster analysis where we're kind of predicting collapse at different temporal offsets. So we're trying to kind of correlate these variables to kind of this collapse time at different temporal offsets. So farther to the left means that at more minutes into the future, we can predict that there's a higher odd or lower odd of collapse, okay? These horizontal lines at the top indicate significant clusters. And what we can see is that already that this effective repertoire decline is an early warning sign of collapse. But this is kind of more of an outcome variable than kind of a process level variable. Whereas what we see that is that specialization is just as predictive, but only one epoch later, right? So what this means is that for up to kind of 9 generations before the collapse, an increase in specialization, or put differently, a loss of diversity is predicting the collapse of these communities. And I think this is a really important lesson here that and it aligns with a lot of work by Peter Turchin and others who have tried to model what types of factors lead to kind of large-scale societal crises as well. Okay, so I'm just going to wrap up here with a summary and open challenges. Here in this tutorial, we try to kind of give you a wide overview of the different tools that social learning can use to learn different settings. We talked about and described methods for social learning, the imitation, where we're directly copying observed behaviors. I also hinted at kind of value-based social learning, where we're not necessarily only using social information to influence our policy, but also influencing our value representations. And a very simple kind of heuristic way to do this is via value shaping, where we add a bonus to socially observed behaviors. But we can also scale this up to kind of more complex forms of theory of mind inference, where we're inferring hidden value representations or inferring hidden beliefs about the world based on other people's actions. And this maybe allows us to kind of unpack it in a more generalizable format. And I think we'll see more of this from Leo and Kartik in the next tutorial. And I've also kind of hinted at some extensions across multiple dimensions of complexity as well, and even some of my work that tries to combine all these together. And so here we kind of arrive at the main advantage of computational models. For each of these mechanisms we can describe verbally, we can also define a computational model that makes more precise commitments to the mechanism's behavior that we're hypothesizing, right? So this allows us to kind of go beyond the vagueness of verbal theories and develop a common language that all of us studying, whether studying animals or humans, studying babies or adults, studying very simple social interactions or more complex collaborations or even more complex cultural evolution, cultural phenomena, we can all have the same common language to talk to one another and share ideas. So through experimentation, through modeling, we can iteratively tweak and refine our understanding of social learning, and here hoping to kind of develop the tools that allow us to kind of interact and communicate to one another. So that ends our second tutorial. We have two more to coming up. So tomorrow we'll have Leo and Kartik teaching us about modeling social cognition in this recursive fashion using Memo. And Thursday I'll be giving the final tutorial on model comparison and robustness. And I think we have